Thank you so much for the introduction. So I'm happy to be here today. As introduced, I'm a final year PhD student currently from Singapore. And today I'm gonna introduce more about my research on the life cycle analysis side of the research on the enhanced rock weathering. So I'm not sure how many people are familiar with carbon markets and carbon credits. Could you help me raise your hand and to let me know? Oh, I got pretty much many more hands than I expected before, so that's good. So basically 1 ton of carbon removal equals to 1 carbon credit. And while we look at the map on the right-hand side, we can see globally it has been distributed everywhere, like for the different market types. We have compliance market, we also have the voluntary carbon market. And enhanced rock weathering usually are more popular in the voluntary market currently. So that means trading based on voluntary purpose. And currently, until fully implemented by 2030, this map is from the World Bank. 1/3 of the GHG emissions will be covered by these carbon markets. So hopefully we will use it as a very helpful solution for our climate mitigation actions. And this map is from the report of state of CDR in 2024. And naming out all of these technologies like biochar, enhanced weathering, they are not really highly ready yet. But all of them, we currently classify them as the novel CDRs. So what will be needed, as I try to address in my research, is to understand the whole life cycle, in the deployment of the enhanced rock weathering projects in real life. So what will really happening in the real world if we want to develop a ERW carbon credit project? The first step is to collect the silicate rock powders, either from the quarries or potentially from the construction wastes. And we will crush them into smaller particle size to increasing the weathering rate via the increased surface area. So during the weathering reaction happening in the soil, that we will aim to enhance the natural weathering from 100,000 years to less than 100 years or even less than 10 years. So the carbon has been sequestered. And some research has shown that this kind of approach can also increase the plant growth and the crop yields. And another co-benefit can brought here is to increase the ocean pH, which means buffer the help on the ocean acidification. So I started a Southeast Asia project on assessing the ERW life cycle analysis and techno-economic analysis. So the graph here I shown is where our field trial based. So all my data are coming from this field trial in rice paddies. And here is a whole research question I want to answer is, will it still be a positive climate solution if considering the whole life cycle in the real life for ERW? So I used the LCA model and also combine it with the life cycle impact analysis model and to do in a spatial distribution optimization mapping. And after all, I got the final results. You will see more details for the model here. So my model has 3 panels. If you look at the middle panel, that means the scenario with ERW. That means we want to use ERW. And the 2 side panels in gray cells, that means without ERW scenarios. So this is a traditional scenario if we don't use ERW at all. So the upper panel, you see the cosine model there will be the input for my LCA model. It will give me the carbon removal rates, which will be depending on the enhanced rock weathering rates based on the chemical reaction on different soil conditions. So we will combine different soil organic carbon, inorganic carbon, microbes as well into this model and get a final result for the carbon removal rate in the soil. And that will be inserted into the LCA model below, mainly on the 4th step, which will be applying to farmland and how much carbon removal can they deliver. And all of the LCA emissions I'm mentioning here are more occurred from the electricity used and also the energy occurred, a fossil fuel used, or to run the vehicles, run the transportation cars, trucks, and all of the stuff. And for the MRV, that will be the lab devices running from the electricity. And also the down panel you see here will be the techno-economic analysis. I incorporated the labor cost and also some like the material cost later on, so get a final result to get a feeling for the cost-benefit analysis. And looking at the left panel in gray cells, that means a traditional scenario. Without ERW, how will we gonna treat those mine tailings? So usually the most popular way is to establish a tailing dam. So when you're constructing these tailing dams, you will also use cement, also use the transportation. Again, emissions occur from there. So the right panel, similarly, will be the traditional farming industry. We will need to produce NPK chemical fertilizers to help plant grow. But with ERW, potentially, we can decrease some part of the chemical fertilizer usage. So the production of the chemical fertilizers emissions occurred there will be potentially reduced from ERW as well. So here are the assumptions for the case study. So the data I'm showing here are based on the 400 hectares of the tropical rice paddy with the deployment of the 10 tons of the rocks per hectare. So this is the final result. We can imagine like the upper panel will be the emissions created through the deployment. And the down panel on the first column on the left side will be the carbon sequestration, mainly through the geochemical side of the reactions, and also combining with rock dissolution and the rock loss. So adding all up, use the upper side to minus the downside, we will get the net carbon removal from a life cycle perspective. So in the 400 hectares of the rice paddy, we can deliver 206 of the net carbon removals, which means we can deliver approximately 206 ERW carbon credits. And seeing that very more interestingly, we can see where does the main emissions occur. That will be the transportation in the blue area. So you can see if we want to make ERW a better solution, then the transportation will be the main part we should focus on to improve and to be optimized. And the middle column, you can see the avoided emission from traditional mine tailing storage. That shows the emissions, embedded emission from the mine tailing to create the tailing dam that can be also reduced more, like 9 times more of the ERW net carbon removal itself. And similarly, for the third column, that would be the emissions avoided from the traditional farming industry via the chemical fertilizer production. So that means not only ERW are delivering net carbon removal by itself, but they also removing through other embedded emissions on the supply chain. So this part, the right-hand side, you can look at it first. It's a case example. I did the spatial optimization in Vietnam. So you can see the red star signs are where the basalt quarries located, and the red dots are the farmlands located. So when I see the top right graph, it will show some white routes, that's potential transportation routes. And we got millions of potential options, and we will choose the minimum transportation distance among all the possible transportation routes and to do the optimization from quarry to the farmland. And on the left-hand side, what we can conclude from here is if we deploy ERW in Southeast Asia, that can save almost 40% of the cost comparing to non-South Asian countries. And the data here might be a bit outdated because I calculated based on last year's data, and will be renewed later. So the second part of this research will be studying on the environmental impact analysis, and based on this model called Recipe 2016. And what it do is to quantify different life cycle steps, as I mentioned before, the transportation, the spreading rocks processes, and the MRV from the midpoint impact categorization and clustered into the end for the environmental damage to human health, ecosystem, and resource scarcity. So it also quantified via the different timelines from the short term, mid-term, until the long term. You can consider long term as an unlimited timeline here. So this will be the result for the ERW lifecycle impact. And you can see the yellow columns are the short term, and the middle one are the midterm, and the purple ones are the long term. And you can see also from here means the human cancer possibilities will be increased if we deploy ERW from the short term to midterm. There is a huge jump. That means the damage will be increased here. And also similarly for the ecotoxicity, for marine side of the ecotoxicity as well. And if we look at this graph, it will show the without ERW scenario regarding the tailing dam construction. So it also shows the marine ecotoxicity will jump even more than the ERW itself from the short term to long term, similarly to the human cancer possibility. And very similarly, the same pattern shows for the chemical fertilizer production. And to get them in summary in these three graphs, for the life cycle impact, we can see the red line here. I'm not sure whether you can see my mouse. If you cannot, then just to see the red line, it will be the mining. It means that more damage will happen in the long term, so it's a drop. And the yellow line will be the farming, the green line will be the ERW. The ERW is quite close to the vertical axis there, but it still caused a bit of damage based on the data. So the green shaded area will be the total impact. That means to use the ERW impact itself minus the farming and the mine tailing impacts. So that means the total benefit we can deliver if you use the data of the area. So that will be the total impact ERW delivered. So my conclusion here will be in the long term, ERW is still a promising alternative for our traditional supply chain activities. And but it cannot provide pure positive environmental impact in the long term. So, and we come to the second project. I would like to really grateful to thank my collaborator, Professor Paul Nelson and Hannah Green, for providing the data based on their field trials in Australia, in North Queensland, on the sugarcane. So we used mill ash and basalt to compare the two different materials of their deployment from a life cycle perspective. And here is our narrowed down LCA system boundary. So this research, as we already sensed from the previous research before, transportation will be a very important factor. So this time we will be focusing more on the transportation itself. So the project system boundary will start from the grounding the rock powders, transportation, and applying for the farmland, and that will be the end. So what we do here to do the optimization of the transportation will be seen on the simplified graph on the right-hand side. We will choose a central point based on the spatial distribution of the farmland calculated by mathematical distribution. And the centroid will be the farmland point we selected. And you see down there and down up there will be quarry 1 and quarry 2. That will be the quarry point we selected. And we will study on the potential connected routes again, connecting the quarry to the farmland centroid points and to calculate the minimum routes. So that's how we do the minimum distance for the transportation. And you can see the numbers behind. We have potentially, in North Queensland, we have 27K more than that potential transportation routes and need to filter from there. And this one will be the real map, what we did in North Queensland. And here we also set different 3 scenarios. The baseline scenario is we just deploy the rock powders, the basalt and mill ash on every farmland we can get on the satellite images. So that will be baseline scenario. And for the first optimized scenario, we need to filter out based on the soil pH. So we filter out of the soil pH, which is less than 5.9 or higher than 8. So that means that in between, these soils could perform better for the ERW carbon removal. And we also have the second optimized scenario, which is considering the transportation distance. Like to use the LCA emission, we only filter the LCA emissions in the end calculated out could be a negative emission, which means the LCA emission will be a carbon removal instead of additional emissions. So we selected those as our final second optimized scenario. And we'll quickly go through the results. It's just, you can see basalt, they performs slightly, delivers slightly like less emissions in total comparing to mill ash. And the main emissions happen will be the transportation. And here, the results will be the net CDR. This is all after after minus the carbon sequestration from the geochemical calculation. So this will tell us like baseline scenario and first optimized scenario, mill ash actually deliver more emissions instead of the removals. So that's one part we should take note of. And this is the cost-benefit analysis. So we can see the basalt cost slightly lower than mill ash distribution. And comparing to other technology like biochar bags, the direct air capture from other studies, we are still remain as a competitive status as enhanced weathering. So this is some calculation graph shown on the right-hand side. I want to deliver the key message here. The enhanced rock weathering CDR potential not only depending on the geochemical weathering rate, but also mainly also depending on the transportation and soil condition selections, as also mentioned in the previous presentations. So here are my take-home messages. In Southeast Asia and in Queensland, Australia, I want to compare more based on my future modeling results. And also considering currently we have some issues for the public exception. So I also want to thank all of the collaborators and my supervisor for supporting me on all the research projects, and thankful to the Dr. Stefan Rialli Geoscience Fund I recently got, and to support my travel to come here in person. So, and based on this grant, I'm also starting a new project on the ERW interviews. So I want to get more stakeholder opinions from this part of the things like farmers or policymakers, and also carbon traders and financiers. So if you have any opinions during the deployment of biochar or enhanced rock weathering in Australia, I would like to learn more from you. Feel free to scan the QR code on the left-hand side to attend in my interviews. So, and feel free to email me or get me connected on LinkedIn as well. Thank you.